We'll wait like 1 or 2 more minutes. A little early still. Okay, so Tuesday we did semi-supervised learning in graphs. Today we're doing unsupervised learning in graphs. And then next lecture, we'll just have to see where it goes. So an announcement. So we've given everybody a 1-day extension on the current homework. So everyone gets an extra 24 hours on that. That was announced on Piazza. Since there are a bunch of people that are still working on the homework, there's no quiz today. So those are kind of like the 2 kind of imminent announcements. Also, so next week, as you guys know, it's a Thanksgiving holiday. You know, we sort of like get together and have a lot of food and find something to be thankful for. So you can be thankful. There's no class. Unfortunately, there will be class Tuesday. So after kind of looking at the schedule, I was going to talk about parameter servers, which is something that's like really important and connected to the last assignment. So the last assignment is basically going to be using parameter servers. Parameter servers are basically another architecture for sort of distributed machine learning. So actually, after reviewing that lecture, I decided to swap because it basically uses latent Dirichlet allocation as one of the running examples. That's the talk that sort of set up. So I'm actually going to switch that. I'm going to talk about LDA, and it's going to be basically an introductory lecture on latent Dirichlet allocation. If you can't make it next Tuesday, I probably won't have a quiz on Tuesday. So you'll probably be okay. LDA, something that's been around for a long time. It's basically an intro lecture on that. And then after Thanksgiving, I'll jump into the parameter server stuff. So that's sort of like the slightly revised schedule. I'm also not having office hours next Monday for totally unrelated reasons. So also, if you're an 805, at the beginning of class, I said I would have oral project reports if time permitted. So I'm going to do that. It'll be the Tuesday before the final exam. So the last Tuesday of class. I want to encourage all the 605 students to attend. And I'm also probably going to spend some time, maybe just a few minutes at the end, but I'm going to spend some time doing a review for the final, just like I did a short review for the midterm. So if you're in 805, there are 5 different projects, multi-person projects. I'm going to allocate 12 minutes to each. Okay, you'll send me the slides, so we should get through this sort of comfortably. And I know that this is sort of not the final report because the actual written report is like due almost a week later. But it will be sort of hopefully a valuable kind of like checkpoint. And you certainly should have something to talk about a week before the end of a semester-long project. So that's the plan. When you're doing a project presentation in your project group, so I think most of the projects have more than one person. It's not in any way necessary that you all speak. You can sort of like talk tag team if you prefer. With a shortish presentation, it may be easier just to pick one person that's sort of comfortable giving talks and have them, have him or her kind of talk for everybody. Everyone's going to get the same presentation grade. Okay, so that's it for announcements. 1-day extension, no quiz today. Project reports on Tuesday, last Tuesday of class, and I've updated the syllabus a little bit. Okay, so today I'm going to talk about unsupervised learning in graphs. It's going to be kind of a focus on techniques which are related to spectral clustering, and also a focus on techniques that turn out to be very scalable. And later on, it's going to kind of tie back to the semi-supervised learning on graphs as well. So I'm going to start out with a particular view of something that's called spectral clustering. How many people have studied spectral clustering? Okay. All right, so this is new for most people. That's good, that's kind of what I expected. All right, so this is going to be like a gentle introduction to spectral clustering, as gentle as you can be. It's kind of mathy. So here we have a graph. Okay, I've got a bunch of nodes connected by edges. So one way of representing this is with a matrix. And if it's a sparse graph, in other words, most nodes are not connected to most other nodes, then it'll be a sparse matrix. So I've got one row and one column for every node in this matrix. And I've got a 1 if there's an edge between those guys. All right. So there's a 1 here indicating that A is connected to B, another one here saying that B is connected to A. I'm just going to be looking at symmetric matrices here today. All right. And similarly, this guy right here means that which node is connected to which other node. What are the two connected nodes? This one right here. E and F, right? E and F are connected. All right, so that checks. So this is how you take a matrix and associate with a graph, or take a graph and associate with a matrix. All right. So it's often the case in realistic settings that these graphs have some sort of structure. So one very common structure is something called a block stochastic graph or a block stochastic matrix. All right. So what do they look like here? All right. So this graph is almost block. It might be block stochastic. Essentially what it means is there are these latent clusters of nodes, right? And within those nodes, there's some relatively high probability. In that cluster, there's a relatively high probability of interconnection. And across clusters, there's a low probability. So here, there's sort of 3 different clusters. Okay? And if you look at the matrix, you can sort of see that. I've actually made this a little bit more blocky, so we can sort of see this kind of clearly. All right? But here we see a bunch of things that are all connected with each other. It's almost a clique, but not quite. Right? Here's a bunch of things that are almost a clique, but not quite. Right? And then there are a few other points here. So it basically looks like a series of blocks, right? Square blocks. I'm not counting the diagonal here because I'm assuming nothing's connected to itself. But other than that, it looks sort of like square blocks with a little bit of noise added. And the noise is sort of the edges between 2 blocks, or the cases within a block where you sort of are missing an edge. Okay, so I should point out that most of the time you can't just look at the matrix and see those blocks. Right? We can only see this visually because I put ABC, one of the clusters, together, and DEF, the next cluster, together, and GHIJ, another cluster, together. So I carefully ordered these things, cluster 1, cluster 2, cluster 3, so they look like blocks. If I shuffled everything, you wouldn't be able to see it. So even if something is block stochastic, if you look at this matrix, you can't necessarily see it unless you've carefully ordered the nodes. All right? But given that ordering, we can sort of see that these are these blocks. All right? So again, the basic idea is for every node, there's some latent class that's associated with it, and there's some fixed probability, which is relatively high for connections between elements of the same block. All right, and then there's some other probability, some low probability for links between things of different blocks. So this is a generative model for a graph, and it will lead to a matrix that looks a little bit like that. Okay, so that's the first part, matrices and graphs. Okay, so here's the next part. So Tuesday, we spent a lot of time talking about label propagation schemes. So in label propagation, you take some quantity that you associate with each node, and then you do something to basically propagate those labels to the neighbors. Okay, so that's a matrix operation, or you can describe it basically as a matrix operation. So let's just associate a scalar with each one of these nodes, right? So I'll assign A, B, and C to 3, 2, and 3, okay? And then let's take this matrix, all right? So this is a column vector. I want to take that column vector and multiply it by this matrix, or the matrix and multiply it by the column vector, however you want to think about it. So what's going to actually happen? So this guy, right, when we multiply this out, we're basically going to put in this element for A, right, we're going to put this quantity, A times A, which is a 0, plus this quantity, which is a 1, times the weight for B, and this quantity times the weight for C. And I guess we also have this one times the weight of F. That has a weight of 0 in this vector, okay? This vector is sparse, so that will be a weight of 0. So at the end of the day, this is sort of the weight I'd associate with A, right? And this is the weight I'm associated with B and the weight I'm associated with C. So notice what's happening here. What we're doing is we're basically taking the values associated with the neighbors of A, right? And that becomes the new value of this vector associated with A, all right? So this is basically doing what we did in our algorithm. It's propagating the weights from the neighbors of A to A, and similarly the weights from the neighbors of B to B, and so on and so forth, okay? So that's what's happening. You might want to take this matrix and normalize it somehow. So I'm going to talk about cases where the columns are normalized to 1. That's sort of the particular case I'm looking at. So what does that basically mean? All right. So what that basically means here is that when I'm doing this propagation step, what I'm going to be doing is I'm going to be looking at again, a weighted sum of the neighbors of A, and that's going to replace the value of A, okay? Now it's just that that weight is a little bit different, okay? So that weight is, in some sense, it's distributed among the neighbors in A, all right? So what's actually happening here? So in this sense, in this little equation, what I'm doing here when I go from V1 to V2 is I'm replacing the values at A with a weighted average of their neighbors, where this weight is basically the a weighted version of the connectivity matrix, okay? All right, so this is very closely related to this weighted averaging operation that we talked about last week in the context of the harmonics functions algorithm, all right? Okay, so this is how we write like a weighted averaging. All right, so now let's think about what that does, okay? So we've got this matrix, all right? We're multiplying by a vector, all right? So let's imagine I do that, okay? So I've got a scalar number that I've associated with each of these points. All right, so one of these days I'm going to draw like a 3D thing that you can like rotate and stuff. But for now, just imagine for each one of these points, okay, the scalar value just is sort of a projection out from this screen toward the audience. Okay, so you've got your 3D glasses. Each one of these has got some projection going forward. All right. And then what I'm doing when I apply this matrix operator to those values, okay, is I'm going to basically replacing every node with the weighted average of its neighbors. Okay, so all those scalar values are going to move around. Okay, so an eigenvector, you guys probably know what that is. So an eigenvector is a vector where if I multiply it by w, then I'll end up with just a scalar multiple of the original vector. So if I had a vector that weighted all these nodes, right, that would be sort of a z dimension. It's like sort of how far they go out into the room, okay? And then if I multiply by w, so I take the weighted average, then if it was an eigenvector, if I happened to choose my weight so it was an eigenvector, then what that would basically mean is that afterwards, the relative positions of the nodes wouldn't change, right? So they might all kind of creep out toward you a little bit, which would be kind of exciting if you were wearing 3D glasses, or they might sort of recede a little bit closer to the screen. And that would depend on this constant lambda, the eigenvalue of that eigenvector, okay? But they would all be sort of relatively the same, okay? So let's just ask yourself the question. Supposing I had a matrix which was like this, kind of a block stochastic matrix, so approximately a bunch of kind of discrete subcommunities that are closely connected, right? And supposing I said, all right, now your job is to pick the vector which is an eigenvector. So it's supposed to have this kind of fixed point property. After averaging, it sort of doesn't change the relative values. So what would that vector look like? so here's one that's like an even kind of blockier thing, right? So here, these are almost all cliques, all right? And there are almost no connections. So it's a very, very clean block matrix, right? So for this, again, supposing I wanted to do it so basically the ordering doesn't change, what would those values look like? All right. So there's one really easy thing I could do that would guarantee I had an eigenvector, okay? I could just put everything exactly 8 inches away from the screen, or 7 inches, right? Or 9 inches, right? So basically, whenever I average something with its neighbors, the average is always going to be 9, okay? The weighted average will always be 9, so nothing will change, all right? That's an eigenvector. It's not really very interesting, but it's an eigenvector. So if I didn't give you credit for that one, what properties do you think the eigenvector would have? So I'd argue that probably, like these dark blue ones, should have similar values, all right? And if they did have similar values, when you average them out, they'd sort of stay kind of nearby, right? If they didn't have similar values, then it would be, since they're all kind of closely connected, when you do the averaging step, the orders would probably change, right? So that's sort of an informal argument, but maybe you can sort of look at this kind of picture and say, yeah, if I was going to replace everything with its average, it kind of makes sense that groups of kind of closely connected nodes should have similar values, right? So I mean, it might work to set these guys about 3 inches and those guys about 6 inches and those guys about 2 inches. Who knows, right? But it seems like probably there would be approximately a mapping between the scalar value and these latent blocks. All right, so that's kind of an intuition. And in fact, it turns out that intuition is not too bad. Here's another picture. So this is from a famous paper by Shi and Maya from 2002. And this is another graph. And I'm just showing you the adjacency matrix here. So the light squares have a heavy edge. The black squares have no edge. So we have a bunch of things up here that are kind of closely connected, almost a clique. A bunch of things here that are closely connected, almost a clique. And then in the middle, we have another thing, which is not really kind of quite a clique, a little bit messier. All right, but that's what the matrix looks like, okay? And it corresponds to a block stochastic graph. All right, here's what the eigenvectors and eigenvalues look like. All right, so first, here's the eigenvectors, okay? So there's one kind of boring one, which is just a horizontal line. Let's skip that one. And that has an eigenvalue of 1, right? So after I do this averaging, it doesn't change the value of that at all. So that's the first eigenvalue, the first eigenvector, the one with the largest eigenvalue. It turns out the next one is these green points. So let's explain what that means. So each row here and each column corresponds to a node. So I've just, under each node, so an eigenvector is, of course, going to assign a scalar value to every node, right? So under every node, I've just graphed its scalar value, right? So these green points here are the scalar values that the second largest eigenvector assigns to these nodes, all right? It has a slightly smaller eigenvalue, all right? So normally you think of eigenvectors that's ordered by eigenvalue. So the first one's the largest, the second has a second largest eigenvalue, and so on. All right, so this green one is basically the second eigenvalue, the first kind of non-trivial one. And you can see what it's done is just what I said, right? So it's assigning roughly the same value to the things in this first cluster, roughly the same value to the things in the second cluster, and kind of the same value. I mean, there's a bit more variation because it's messier, right? But roughly the same value to things in this middle cluster, okay? So this is what these this eigenvector looks like. The next one is kind of similar. The next one is these red points. All right, so it gives roughly the same value, really, to almost everything except for the things in the middle here. Okay. So there's kind of two things that are interesting here. One is, if you look at this graph, there's a lot of structure that kind of jumps out at you, so you can sort of see these three categories. And sure enough, there's sort of some structure. There's in this list of eigenvalues. There are a couple of big values, and then there are a whole bunch of really small ones, and there's sort of a gap in between. So sometimes it's called an eigengap, so you might look at that and sort of see how much structure is in your matrix. And if you want to approximate this matrix, you might do it by combining these first few eigenvectors. So the other thing is that there's sort of some structure that's suggested by these nodes, by these values that we've associated with these nodes. So let's think about what we can do with that. So here again, these are these two interesting eigenvectors, right? So so this one right here is assigning a bunch of nodes a value of around 0.2. Okay, and those same nodes get a value of maybe around 0, okay, by the red eigenvector. Okay, so if I decided to basically just take each of these nodes and plot them as a point in k-dimensional space where I've got one dimension for each of the eigenvectors, then I'd end up with something like this. So these guys, they're about 0.2 in the the green dimension, right? And they're more or less around 0 in the red dimension. Okay, so I get a bunch of points that were plotted near each other because they have similar eigenvalues, right? And then going on, right? The things in this next cluster, right? They would be a little bit more spread out, but they'd be somewhere around here. Okay, so the first eigen values. Those tend to be sort of, somewhat negative, maybe around, negative 0.4. I just did these by hand, not systematically. I should have done them systematically. But there's just a picture from a paper. I didn't have the actual numbers, right? And the y value, the green value, is sort of between 0 and negative 2. So that's sort of where they are. Okay, and this is the other cluster. Okay, so if I basically take points and I map them into this space that's suggested by the eigenvectors, then I can also see some structure. Okay, so let's just think for a second what a beautiful thing this is, right? If you want to do unsupervised learning on a graph, let's say you want to cluster the nodes in the graph, how do you do it, right? I totally know how to cluster like points in a low number of dimensions, right? I could take those things and just run k-means or a mixture of Gaussians or really, any one of 100 algorithms that people have proposed over the last few years. But you can just run your favorite normal clustering algorithm here. It's not obvious how to use those on a graph, okay? But if I take the graph and I reformulate it like this, if I look at the eigenvectors of this weighted adjacency matrix, and then I use those eigenvectors to map each node in the graph over to this low dimensional space, now I've got something I can run clustering on, okay? So this is the key idea in spectral clustering, okay? So the math behind this basically says if I've got a graph that's fully connected, but roughly block diagonal, and it's got k blocks, all right, then, and W is this weighted matrix, okay? The top eigenvector is a constant, all right? The next ones are going to be roughly like this. So they'll be roughly piecewise constant where the pieces correspond to the latent blocks. All right? So this is the spectral clustering algorithm. We know this to be true. So all you've got to do is take the top k eigenvectors, which you may not know how to do off the top of your head, but MATLAB and lots of other programs know how to do this, right? So you can just compute the top k plus 1 eigenvectors, and the top one is a constant eigenvector. That's not interesting. So just throw that one away. And then you use the next ones from dimension 2 to k plus 1 as dimensions that you're going to embed these nodes in. Okay, so every node A, you construct a vector where each component is the value given to that node by a particular eigenvector. All right, and then you cluster. Okay, so k-means is one reasonable thing to do. Okay, so this has a lot of advantages. It's really pretty. There's no local minima involved. Okay, well, I guess there's local minima involved in k-means, but there's not a lot of local minima. When you have these things that are kind of block diagonal, when the relations are kind of roughly transitive, which is often the case in a lot of social network settings or social network-esque settings, then it works pretty well. Okay. So from scalability point of view, it's not ideal. So computing the eigenvectors, there's lots of work on doing this quickly and efficiently. So you can scale up. There are all sorts of kind of clever algorithms for doing this more quickly. They're still not that fast. So eigenvector computation is a bottleneck. There are lots of algorithms that will compute the top k eigenvectors, for some value of k that you give it, without computing all the other ones. But even that can be a little bit expensive, and a lot of the fastest algorithms are approximate, and as we can see, that actually causes some problems. So it's also, like I said about some of the algorithms in this class, like the count and sketch, my experience is it's actually a little bit finicky. So if you choose the wrong number of eigenvectors, then you get poor results. So sometimes you've got a data set which clusters beautifully in some subset of the top eigenvectors, but not the first few. So sometimes it's sort of a kind of noisy dimension, or a couple of noisy dimensions will creep in to those top few eigenvectors, and then you can get sort of unstable performance. And in fact, as for many unsupervised learning algorithms, sometimes the performance can sort of just drop and go from really good to very terrible when you just have some sort of modest change to the data set. So just to give you an idea, here are some experimental results. So these are two different spectral clustering algorithms. This is the one I just told you about, basically. This is the Shi and Ma algorithm. And what we did is we took a whole bunch of graph data sets here. So these blog data sets you might know. Most of these other ones are constructed by essentially building a graph, which is a k-nearest neighbor type graph, as we talked about for similarity, semi-supervised learning. So you take the nodes in a data set, the instances in a data set, and you connect them up if they're close to each other. So this is a collection of different graphs. And what we did is these are actually started out as classification problems, so we have a known label. So we run the spectral clustering algorithm with the right number of classes. So we know how many classes there are. It's usually 2, 3, 4 for one case. And once we've done that, so we run k-means with the right number of clusters and picking the right number of top eigenvectors. And once we've done that, we basically look at how accurate it is with respect to the best possible mapping of the class labels to latent clusters. All right. So sometimes it's perfect. Okay. So distinguishing between 0 and 1, very different looking digits, it's perfect. Okay. There are lots of other cases where it does really good. So this is a 20 newsgroups case. Two classes, it does really well. There are some cases where it doesn't do well. Okay. So these are two similar data sets, both blog data sets. This is the one you guys used. It does terrible. All right. This is a slightly different one. It's a little bit smaller. It does great. One thing which I found very disturbing when we were doing these experiments, by the way, I should say Frank Lin did these experiments, my former student. One thing I found really disturbing was that if you took a subsample of this endemic glance blog data, then it did really well. If you add all the data in, there's just a little bit too much noise, and it does terribly. So essentially what happens is the informative eigenvectors are no longer the top two, so it sort of fails. All right, so even on cases that are really well separated, like these things, sometimes the spectral clustering method doesn't work, but it often does work pretty well. All right, so that's my gentle introduction to spectral clustering. Questions? In the back.
In general, I mean, if you see clustering, it is like unsupervised without, right?
Yes.
So once you have clustered, what is the measure of knowing that you are closer to finding the true number of clusters?
So why am I saying, so why in the experiments do we assume we know the right number of clusters? Is that the question?
I mean, what is the point here? Because you already know the clusters.
Well, you want to, so we do know the clusters. Okay, so really, in real life, you'd want to measure, you'd want to use some sort of supervised learning for this or semi-supervised learning or something. But if you're evaluating an unsupervised technique, how do you do it, right? What do you do to evaluate an unsupervised technique? You want to have some sort of quantitative measure. And there are some things you can do. You can choose what it's trying to optimize. You can look what it's trying to optimize and see how well it optimizes that. You can look at how well it performs computationally. Is it a fast algorithm or a slow algorithm? But if you want to see what does it come up with sort of reasonable clusters or good clusters, a pretty common experimental procedure is to take some data that's been labeled somehow with kind of real clusters and see how good it is at constructing those real clusters. So here we've made the problem easy in a lot of ways, right? We've told it exactly how many clusters it needs. And we've also looked at some problems which are similar except that they're, it's harder to tell the difference between 1 and 7 than between 0 and 1. So we're looking at sort of systematically different classification problems, and we're trying to see what we can see about these different methods. So that's the basic idea. Follow up? Yeah.
Particularly spectral clustering, will it be affected by the relative size of the clusters themselves? Say, for example, one cluster has only 50 and another has maybe like 5 billion.
Yeah, so if you have clusters that are really unbalanced in size, does that make it harder? It does, in particular because a lot of these algorithms are sort of assuming that you're going to have somewhat balanced sizes. In these cases, the clusters are all relatively well balanced. It certainly gets harder when you're looking at small subclusters. So yeah, the local partitioning method, I guess, is sort of one thing to think about when you're looking at trying to find subclusters that are sort of small in some specific area. But again, we're basically sort of trying to see how well these techniques work. So they're far from perfect as they are, okay? And we've still sort of made this as easy as we can. Well, not as easy as we can, but we made it easy in a lot of different ways. All right, so this is sort of kind of like picking at sort of the boundary of where these unsupervised methods work. So they work pretty well for some of these things and less well for others, right? And we can sort of, kind of predict, if we add more classes, right? Or if we increase the difficulty of the decisions that it's making, we can predict the clustering will get harder, and it does. Okay, so that's kind of the point of these experiments, just to sort of see how well they do at sort of reconstructing these known classes. Any other questions? All right, so let me talk to you about another completely different way of thinking of the question, okay? So we can also think of this as an option. Okay. So let's see. Here's basically the question. All right, we're going to start with this question. Okay. So let's say what I want to do is I want to partition things into two sets. So it's clustering, but they're basically just two clusters. Okay. And the way I'm going to do that is I'm going to assign a latent value to each, a scalar value to each node, and it'll either be +1 or -1. Okay. So those are the numbers I'm assigning to everything. Okay. And this vector y basically is an indicator. It's going to split the new nodes into those two sets. Okay. So here's something that we can sort of like sit down and analyze. We're going to look at this formula right here. So this is y transpose times y. Okay. And in the middle, so that's like sort of the inner product of y with itself, right? And then in the middle, we've got this matrix right here. So it's D, which is the diagonal. So it's basically the sum across every row minus A, which is the adjacency matrix. Okay. So D is basically it's a diagonal matrix, which is the row sum for every the sum of outlinks for every node. Okay, and A is the adjacency matrix that we started with before normalizing it. Okay, so what does this look like? So I just want to say before I go on, this construct here, D minus A, is actually really important in kind of spectral graph theory. It's called the Laplacian. Okay, I don't. It seems like a fancy name for just a simple thing, d minus a, but that's what it is. So here's some math. Okay, so here's y transpose times d minus a. Okay, and of course we could write this as follows. We can just sort of distribute. So we've got y transpose d minus y transpose a. Right, so these are things that are kind of easy to think about. It's basically sort of a stretched inner product where we're stretching it by a matrix here. Okay, and we can write this out too. Okay, so d is the diagonal or degree of each node, so it's the sum of the outlinks from each node. All right, a is the adjacency matrix. Okay, so this quantity right here corresponds to this sum, and this quantity right here corresponds to that sum. Okay. So now I'm going to do a couple of things. So the first thing I'm going to do seems totally senseless. I'm just going to multiply by 2 and divide by 2, right? So that doesn't change anything, obviously. But it helps me a little bit. What I'm going to do is I'm going to take this thing right here. I'm going to split it into 2 different parts, okay? So D, which is a diagonal matrix which corresponds to the degree. As I said, that's just the sum of the outlink, so it's this quantity right here, that's di, all right? And we can write this 2 different ways. I've got 2 copies of this. I'm going to write it 2 different ways. I'm going to write one with, indices going this way and one going with the indices going that way, right? It doesn't really, things are obviously kind of equivalent, but I've got 2 copies of it, so that's okay, right? So I've got these things. And now that I've done that, I still have this, right? That's copied over, all right? And I'll just copy that over again. Now that I've got these things, you can sort of like take a look at what these are, right? So we can take this, the sum of the a's, and pull it out here. And now I've got this quantity, these 2 quantities, okay? So this is with the i's and this is with the j's, all right? So this is kind of interesting because we can recognize this, right? This is basically a quadratic. Okay, we've got yi, yj, yj, times minus 2. So it's basically this quantity right here. Okay, so this turns into this quantity. All right, so let's think about what that is. Okay, so remember in our semi-supervised learning, what we're looking at is, well, we want smoothness. So we want some sort of penalty for giving different labels to things that are on opposite sides of an edge. All right, so here we're summing over all the things that are on opposite sides of an edge, okay? And we're looking at the difference in their labels. So that's going to be 0 if we've got 2 things that are connected and have the same label, and it'll be 1 otherwise, okay? So this is basically the energy function that we try to minimize in the harmonic function. So sometimes this is called the cut for y. If we take this whole thing and we normalize, so we look at, instead of the degree minus the adjacency matrix, we look at the identity matrix minus the normalized version of the adjacency matrix. That's called the normalized cut, or n cut, okay? So this is another kind of important way of kind of thinking about this, right? So essentially what spectral clustering is trying to do is it's trying to find a y that minimizes this quantity, all right? And again, I guess this is called the normalized Laplacian, okay? So this quantity right here is a kind of a reasonable measure of the energy of a set of labels, all right? So it turns out we can minimize this numerically, okay? So to minimize this numerically, we want to find the smallest eigenvector. In general, to minimize this quantity, we want to find the smallest eigenvector of x, all right? But that's not necessarily satisfying the constraint that each thing is either +1 or -1. These things will be any real numbers, so it's sort of a relaxed solution, all right? It's some approximation to minimizing that energy function, okay? So this is sort of another explanation of this the Xi and Mella algorithm, where we essentially use these first few eigenvectors. So if we did this in just 2 dimensions, just 2 spaces, okay, then what we would see is we'd see something that was sort of an approximate split. So we would be assigning everything a value, and then we would threshold that value at some point to choose 2 clusters. Okay. So this is actually the normal way to think about spectral clustering. Okay. Every tutorial, every intro to spectral clustering kind of talks about it this way as a relaxed optimization. I don't tend to think of it this way. I actually kind of like the averaging view. And part of it is because it sort of seems a little more intuitive to me, and partly because it leads to some techniques which are much more scalable. So before I move on, more questions? Okay, so this is another technique. So this is a variant of spectral clustering that's like way, way faster. And again, it goes back to this averaging idea. We have a graph, we turn it into a matrix, we take that and normalize it, and then we're doing this process where we just do averaging. Okay, so this is kind of a simple algorithm to think about. All right, the algorithm that we come up with is we start with some initial vector, maybe just a random one, and then we update it. Okay, so we replace everything with a weighted average. All right. So what I'm going to do is I'm actually going to look at the dynamics of this process. Okay, so I kind of know what this is going to do if I take this and iterate it over and over and over again. Okay, so this is power iteration. Power iteration is known. It will just converge to the largest eigenvector. So if I do this, eventually we'll converge to the largest eigenvector of this matrix, which is constant. All right, so at the end of the day, after I do all this averaging, we're just going to end up with a constant for everything. But let's go ahead and just do that for the heck of it. Okay, so we know this is sort of an interesting algorithm. If we add clamping for the labels, then we come up with a harmonic function algorithm. But let's just sort of see what this does. Okay, we know asymptotically it's going to get to a constant, but let's just take a look at what it does. So here's a picture. So here's a graph. All right, and this is the sort of graph that would be hard to cluster. This is a sort of a data set that would be hard to cluster with k-means, right? So if you tried to call these, sort of map these to a small number of clusters in this space, it wouldn't work very well. But we're going to take this and we're going to describe this as a graph. So these blue points, we're basically going to link everything I'm going to link everything to everything else in the graph, but I'm going to weight it by distance. So these blue things are closely connected to each other. And then these green things, well, each one is sort of closely connected to another subset of green things, right? And then at some point, it kind of wraps around. There are a few connections between the green and the blue, but not that strong. And then we get something sort of similar for the reds, right? So that's the graph that we have, okay? And what I'm going to do is I'm going to start out just assign everything a random number, all right? And then I'll do this repeated averaging, okay? So I'm going to do this for 10 steps. And what I've done is I'm going to start out, I've ordered all these nodes by the segment they're in. So the colors are basically just the Y position. So don't look too much at the colors right now. But the blue segment is this part right here, and the green segment is this part right here. And the red segment, which is larger, is sort of the second half of it. All right, so after 10 iterations, we get something like this. All right, so that's actually kind of interesting, right? What's happened is we are converging to a constant, but the blue things converge to a constant much more quickly. And that makes sense. They're very, very closely connected, right? And then as I iterate, so this is 50 iterations, 100 iterations, we can sort of see the blue things stay apart, but what happens is eventually the red and green things just sort of start to separate. So after 400 iterations, you're getting this, okay? So I should mention, okay, this is converging, okay? In this picture, I've scaled everything to be the same vertical distance. So really, this vertical distance starts out large, right? And then it gets smaller, right, and smaller. And at the end of the day, it's very, very small, okay? But also at the end of the day, what you see is that it's not quite converged, right? If you look at the first 4, 5, or 6 significant digits, it will look like it's converged. But after those digits, what you see is something that's really significant, all right? What you see is that there's a clear separation between these different communities, all right? So this is the dynamics of that averaging process, right? And this suggests an algorithm, okay? So it's basically repeated averaging with some early stopping, okay? So we start with some initial vector. We repeatedly average, and then we normalize that vector, okay? So we don't want to run this to convergence, so we know we want to stop. I guess the simplest way you could stop is you could look for a case where the difference between two vectors, vt and vt minus 1, gets small. And it turns out that doesn't work too well. Instead, what we do is we look at cases where sort of the velocity of change starts getting smaller, okay? So you basically look at two adjacent differences, right? So that's basically learning rates, all right? And then you look and sort of see whether the acceleration has sort of dropped. When the acceleration gets close to 0, that's when you stop, okay? So, so this is the algorithm. The degree matrix is a sort of reasonable non-random starting point if you want to get something that's very predictable. It's easy to implement. Of course, we can do this averaging very easily on a system like Pregel or GraphLab, and we can also do it very quickly in MapReduce. It's kind of interesting. So the embedded space in the next few experiments, I'm going to show you, it's all just one-dimensional, right? So really, this is just a scalar vector. And then what we're going to do is once we've done this, we're going to take the results in that scalar and then do clustering. So we're clustering in one dimension. When the problems get bigger and harder, we might want to add more dimensions to this. But like something on the order of like 4 random dimensions works actually pretty well. So here are the same data sets that I talked about before. So some of these have sort of a natural graph structure. Some of them you're looking at cosine distance between instances. So it's kind of this nearest neighbor graph. And I showed you these numbers before. Okay, so this is the performance of these spectral methods. And one thing which is nice is there were a bunch of cases where this technique where the spectral methods failed, and this one doesn't. Okay, so it seems to be a bit more robust, and on average it works better. And these are, like I said, these are sort of other cases where you get sort of a surprisingly big drop in performance when you make a relatively small change to the data set. So this is basically going from 200 documents to 400 documents. So by all rights, that should be an easier problem, okay? But the spectral methods have trouble with that. So they actually see a drop in performance even though you're getting more data. So we get a little bit of a drop in performance, but not nearly as much. And here's some other numbers. I mean, these are all small problems, so it's okay to run the spectral methods on these, so you can do the eigenvalue decomposition. But the runtime still goes from like minutes to milliseconds. So it's much more scalable for a decent-sized data set. Okay, so are there questions about what this algorithm is? It's super simple, okay? So I'm going to talk a little bit about some other experiments. So these experiments are basically on synthetic graphs. So here we're varying the number of clusters, okay? We've got pick with a random starting point. That's that dotted black line. This is pick with 4 random dimensions to start with, okay? And this green line is the one that does best. And it's essentially a probabilistic model that kind of expects this sort of data, okay? So these are 2 different synthetic graphs. And the probabilistic model does do best, but this pick algorithm actually works very closely and often better than the spectral methods. Okay. Yeah, this is the same thing with noise. This is the same thing on a whole bunch of different network data sets. So these are a whole bunch of different social networks. So this is the holistic model, which does pretty well. Okay. This is picked in one dimension, which starts out as the degree of a node. And the reason that's kind of reasonable is you'd like to start out with something where the scalar value you assign is different for things in different clusters. So different clusters, if you're connected according to some probability, the degree of a node in that cluster is probably related to the size of that subcommunity. So if you're part of a big subcommunity like machine learning, you know lots of people. If you're part of a really small community, like let's say, I don't know, non-monotonic logics, you probably have fewer colleagues. So the degree will sort of be a weak signal of what cluster you're in. So that works pretty well. This is with 4 random starting points, and these are these fancy spectral methods. This is yet another problem. It's a little bit further off. You're basically clustering people in a citation network, and that sort of true label is which person this is. So we've got a bunch of people whose names match C-Chen. We know what their real identifiers are, and we sort of merge them together, and we sort of try to disambiguate or untangle those. So again, there's lots of variation in these things, but this method sort of seems to work pretty well on average. Okay. So that's the pick algorithm. There are some pointers to papers on that if you want to look. Now I'm going to go from this to talking about another problem, which is basically using these techniques for data sets which are not intrinsically graphs. Okay, so we've already done this, right? I started out with a data set that wasn't a graph. This example here, right? So this is not a graph. This is just a bunch of points, all right? And then what I did was I created this graph here, okay? So I connect things to their nearest neighbors, or maybe I connect things to everything weighted by the distance, okay? But I'm taking a non-graph data set, I'm turning it into a graph. And there's some good reasons for wanting to do that. So this graph data set would be hard to cluster using traditional methods, but it's easy to cluster in the spectral space, okay? So PIC handles it beautifully, and things like NCUT would also work pretty well for this, okay? The original paper on spectral clustering was full of little examples like this. So you have things that are sort of transitively connected that those compose the clusters, but the way those transitively connected things are intertwined with each other might be sort of complicated. It's often useful to apply these methods to non-graph data set, okay? So one data set we might want to think about is just maybe, let's say, text, okay? So we can take a large data set that has discrete feature values, let's say words, and make a bipartite network. So the network has 2 types of nodes, documents and words, and there's a link if a document contains a word. So concretely we might have documents that are maybe email messages, and then we'd have other nodes that are like words in those email messages. Okay. So in the experiments I talked about just a few minutes ago, the edge weight we were using was the cosine distance between all pairs of classification instances. So it wasn't a nearest neighbor graph. We basically took every pair of instances and computed the cosine distance. All right. That gets really expensive really fast. Okay. That's obviously a quadratic operation. Okay. So that does not scale. Right. So we can compute a k-nearest neighbor graph, and in fact, earlier this semester we talked about some, fast, scalable algorithms for computing these, the heavy-weighted edges, but it's still a somewhat expensive thing to do. Here's another idea, okay? So what we're doing basically inside is we're doing this propagation step, okay? So what we're basically doing in our algorithm is we're repeatedly taking a vector and we're multiplying it by W, okay? W looks like this. It's basically the adjacency matrix with some normalizer, okay? So D here is basically the degree, the inverse of the degree, the number of edges, or the total weight of the out edges for node I, okay? So this is W, all right? So it has a little bit of structure. It's the adjacency matrix times this degree matrix, okay? So this is what we're doing over and over again. This is our whole algorithm, okay? We're going to take a vector, we're going to multiply it by A times D inverse, all right? Let's think about kind of basically getting rid of all these things, okay? So it turns out there's actually sort of a clever way of computing the degree matrix. I can basically take an all ones matrix, multiply it by A, and that gives me the degree matrix. So this is an all ones column vector, multiply it by A, that gives me the degree, okay? And now let's think about the, what this adjacency matrix really looks like. So what I want to use is I want to use cosine distance for every pair of nodes, okay? Cosine distance with, let's say, TF-IDF normalization is going to look kind of like this, okay? I've got my original TF-IDF weighted vectors, and then I have these normalizers. And I divide through by that, so that's the inner product of those vectors. All right, so that's the adjacency matrix. All right, so I don't want to compute that. All right, if I computed that and wrote it down, it would be huge. It would be size n squared if I have n examples. Right, so I don't really want to compute that. So is there some way I can do this multiplication without actually computing A? Well, it turns out you can. Okay. Let's compute these normalizers. So I'm going to compute this quantity here. So this is a diagonal matrix N, right? And then I'm going to basically have a feature matrix. So this goes from a document I to the weight this goes from a document to a word, and it tells you what the weight is of that word in that document. Okay. So I can tell you what A is, right? Basically, this inner product here, I can write down all those inner products as F transpose times F, and then the normalizer, we've just got N inverse, and I just put them sort of at the beginning and the end here. Okay. So far I haven't done anything. I've just basically given you sort of a MATLAB implementation of this that tells you how to construct this matrix, but I still don't want to construct that matrix, okay? So what are we going to do? So the basic idea is the following, all right? If I want to compute the degree matrix, what I can do is I can compute it by just taking this and multiplying it by the adjacency matrix. The adjacency matrix looks like this. So the degree matrix also looks like this, right? And the key thing here is that the way I compute this makes a big difference. If I compute this matrix first, right, that's an n by n matrix. It's really expensive, right? But this is just a vector. So I can take that vector and multiply it by this diagonal matrix. That's no problem. Then I can take that, I can multiply it by F, no problem, right? Then I can take this and multiply it by F transpose. Again, no problem. Right? So essentially what I've done here is I've taken this ones vector, I've looked at the vector normalizers, I'm basically taking those weights and pushing them over to the features, then pushing them back to the documents, right? Propagating them back to the documents, and then I'm doing another normalization step, all right? So that's the degree, okay? And I can use the same trick when I'm doing this update, okay? So I'm taking a vector and I'm multiplying it by A. All right, this degree thing is just a diagonal. I can just compute that once. All right, and when I do my update, I can basically take this vector, again multiply it by n inverse by f transpose by n inverse n d. So the key idea here is that we can basically do this computation only using matrix vector products, okay? So I'm doing this propagation as if I had a complete matrix of all the pairwise distances, but that never gets explicitly computed, okay? Instead, everything I'm doing is propagating weights between different matrices. Okay. So that's the key idea. So let's try it out on a bigger data set, okay? So we used RCV1. So we actually used a subset of this. We took all the documents that had just one label and all the categories that had at least 500 instances. So there's about 100 categories and about 200,000 documents. And then we generated 100 random clustering problems, okay? So for each of these, we took 2 categories. And the constraint, actually, there was a constraint that we'd only pick pairs of categories that were roughly the same size. So no category was more than twice the size of the other. Okay, so we're still looking at sort of these relatively easy, balanced, not too many categories problems. And we basically just want to see how well this technique works and look at sort of some scalability issues. All right. So baseline is just picking the most frequent category. Then we're looking here at the average accuracy of k-means. So you just basically take the original documents, you run k-means clustering with 2 clusters, and then you label the clusters the most accurate way. And that gives you an accuracy about 70%. All right. So pick gives you about 77%. All right, and these are 2 spectral methods. So this is using ncut using the actual eigenvector calculation. This is using this is ncut using a fancy, much faster approximate method. So it turns out that approximate method has some nice theoretical guarantees, but it doesn't work so great for clustering in this situation. There's not really a difference between these things, not a statistically significant difference. And in fact, if we start looking at these scatter plots like we did the other day, so here on the left-hand side, we've got the accuracy of pick. The bottom here, we've got the accuracy of k-means. And then here again, this is pick versus the exact eigenvectors, ncut, pick versus the approximate eigenvectors, ncut. All right, so there's 100 points because we had 100 problems, okay? And you can see, so pick doesn't always win. There are some cases where k-means does better, but on the whole, it outperforms it much more frequently, okay? So for ncut, what you see here is that for these data sets, these algorithms really are pretty much the same, right? So almost all the problems are really, really close to that diagonal line. So in most cases, the accuracy is pretty much the same. In most cases, they're getting the same clusterings. And there are a handful of cases where the ncut algorithm does a little bit better. There are a handful of cases where the pick algorithm does a little bit better. We can't really separate these things. I might give the nod to the ncut a little bit, but it's not a significant difference. But if you use the approximation, then it's much worse. So the kind of take-home message is that this is essentially a fast approximation to the normalized cut for these data sets. So how fast an approximation? Well, here's some numbers. So this is the runtime. Now we chose a lot of different data sets, and they just naturally had different sizes because some of the categories are bigger than others. Okay, so we've got a big spectrum of sizes. All right, so this is the ncut time. We predict it to be quadratic. Cubic. We predict this to be cubic. We predict this one to be quadratic. And yeah, this is pretty much quadratic. This is a little bit worse than quadratic, for sure. All right. And the actual runtime, I mean, the one you want to use basically goes up to, minutes, several minutes for the large data sets. You can run it, and this is sort of why we kind of stopped at this point because we wanted to make these comparisons. But it takes minutes to run, and it uses a lot of memory, okay? So pick here, it's like, fits a linear curve, okay? And basically, you're still in milliseconds, right? So nothing took as long as a tenth of a second to run. So that's the timing. All right. Bunch more experiments I'm going to skip because I want to get to the last bit. Okay. So actually, let me just take a break. I'm not in that much of a hurry. Questions? Any more questions? Okay. For power iteration clustering, we noticed that basically the whole algorithm is basically multiplying a vector by a matrix. And then we said, well, if I want my matrix to be pairwise distances, I can break that matrix down and basically do the equivalent computation without ever explicitly constructing that matrix. Okay. But there are other algorithms that are a lot like this. So the harmonic functions algorithm also looks a lot like this. We take a vector, we multiply by some weight. So we do this weighted averaging. All right. And then there's another step where we replace it with the seed values. We just do that a few iterations. So the multi-rank walk algorithm also looks almost exactly the same. So one step of the page rank propagation is essentially a matrix multiplication. We can turn the page rank computation into the personalized page rank computation to the same sort of process. Okay? And if you recall that's basically the way we do label propagation. When I was talking about NEL, I said, well, one thing which is really nice is the variation that we're using in NEL is we basically take examples, we propagate the weights to features, and we propagate the weights from features back to examples, and so on and so forth. So that's essentially an instance of the same sort of trick, okay? And this lets you get basically a scoring of everything according to how close it is to that set of seed categories. Okay. So in another paper, Frank and I basically took that idea and formalized it. Okay. So what we're looking here is we're looking at not doing this particular algorithm, okay, which in NEL is described as co-EM, but it's basically the harmonic functions algorithm. What we're looking at instead is using the multi-rank walk algorithm on this data. So the distance we're looking at here is generally cosine distance. So for the documents, we're using cosine distance. These are some subsets of basically this graph, this NEL graph. Okay, so this one has roughly roughly 10 million noun phrases and around 10 million features, or around 8.6 million features. All right, there are about 120 million non-zero ones. This is one that we pulled up that was a smaller subset, and it was just we just had labels of whether something was a city or not. So it's two classes, one category, plus or minus, it's positive or negative, and that was something we could evaluate a little bit more easily. This has 44 categories, so it's actually a small subset of NEL. But even for those 44 categories, we don't know how these 10 million things should be labeled. It's harder to evaluate performance. So this is basically the size of the data sets. So with sparse matrices, this isn't too bad. It's about 2 gigabytes. And if you look at the size of this trick, the representation we use to use this trick, again, it's quite reasonable. Okay, so the biggest one is like 2.4 gigabytes. If you try to look at all the pairwise distances, things blow up really quickly. right? So for 20 news groups, which has 20,000 instances, you end up with like 5.6 gigabytes, right? For RCV1, it would be most of a terabyte, okay? For this one, it would be 4 terabytes, okay? So those are estimate. We didn't try and do these, okay? And here's some numbers. So this is using multi-rank walk. This is using harmonic functions. This is using support vector machines. This is the number of seed labeled instances. So we're looking at semi-supervised learning here again. This is the RCV1 data set. So again, we're doing okay. The multi-rank walk seems to be doing a lot better in this setting than the harmonic function does. Usually people run that on a nearest neighbor graph. It's not doing quite as well as support vector machines. This is also using random seeds. If you use some clever strategies for choosing the seeds, then you can actually semi-supervised learning that at least starts off faster than support vector machines. So you can actually get a bit of an improvement. And then for these two null data sets, again, we're looking at, so support vector machines don't really work here. The harmonic function works pretty well. The multi-rank walk with a well-chosen distance metric actually works substantially better. So this is one data set that we could sort of completely label. We also did this over a larger selection of 44 data sets, and we sort of like randomly sample. So again, across these data sets, support vector machines is kind of bouncing all over the place, but it's usually worse than the semi-supervised methods. The harmonic function does as well or better on roughly half of the cases, and the multi-rank walk actually does better on about half the cases. So it's kind of a wash overall as to which one is better. Okay, so that's all I got. I guess we have a couple of minutes for questions if people want to ask, but I'll let people go ahead and leave, and the people who have questions to come on up. So I will see you guys on Tuesday.